Oh, we started. Okay. Good evening. Good evening, everyone. And let me begin. So today we are starting with the new unit, which is on rotation. Once again, a few of the viewers, they requested we need to do some more problems on rotation. Actually, I had already started on rotation, which is on your center of mass, but now the demand is more on rotation. And in fact, it has been commented by many saying that rotation is one of the toughest chapters. I totally agree that rotation indeed is a toughest chapter for many. The reason is because there are a lot of applications which comes from, sorry, the applications of rotation, the numericals in rotation are from the applications that you have already learned from your previous chapters. So that's why usually people feel that rotation is one of the toughest chapters. Okay, so now what we will do is let us consider this problem. So the first question here is about identifying the correct parameters in a rotational problem, because it appears that okay, every parameter is very similar and we do some mistakes. So this is one of the problems I have noticed when I give some numericals to my students. So a wheel rotating with uniform angular acceleration covers 50 revolutions in the first 5 seconds. Okay, 50 revolutions in the first 5 seconds. And as a result of it, after the start, find the angular acceleration and the angular velocity at the end of 5 seconds. So what generally students do is 50 revolutions in the first 5 seconds. So what they do is, what is it we need? We need angular acceleration. Okay. So just they consider 50 revolutions per second. They put this value, angular velocity is nothing but 50 minus 0 divided by the number of time amount here. Okay, they put this across. So why we do it is because we consider, the students generally consider that this value can be in the numerator similar to that of your angular velocity, what you have in numerator. Now let us understand what do you mean by angular velocity. Angular velocity is nothing but theta 2 minus theta 1 divided by t. Now what is theta 2? Theta 2 is nothing but the angle. Now how do you describe the angle? You describe the angle in terms of or theta in terms of either radians or in terms of degrees. Now, if something is expressed in radians, you can do it. But now the question is, see, I have something in revolution. And I can easily say, okay, 1 radian, maybe if I say that, if I say one revolution, this can be equal to 2 pi radians, right? One full revolution is equal to 2 pi radians. Now, if that is the case, then what is wrong here? Okay, why shouldn't I do it? So based on this condition, they have just put, instead of putting this in radians, they have put this in terms of revolutions. And here also, this is 0 revolution. Okay, it does not revolve. That initially it is 0. So 50 minus 0 divided by 5, which gives you 10 revolutions per second, which indeed appears to be correct. It's not correct. Okay, I'll tell you what is the reason. And the angular acceleration, what he does is, okay, he takes up this angular velocity, okay, and then divides this by time taken, and finally he gets the answer as 2 revolutions per second square. Okay, appears to be very much right. Then what is a mistake that which a student actually does it? Okay, now towards it, the first thing is when you are describing theta, so here 50 revolutions here. So this is nothing but an instantaneous value here, which you should consider theta is equal to omega I into t plus half alpha into t square. You should be using this. Why this? You should be using this one here, because this is an instantaneous value over here. As a result of it, this should now be equal to 50 revolutions, should be, starts from rest, so it is 0, plus half alpha into t square. What is alpha? Alpha is not known to you. How do we do this? We do not know. I can now write half alpha is not known. First 5 seconds, t is known. I'll substitute this value 25. So what happens here? 25 ones are 25 twos are. Now what do I have here? I have 2 is equal to half into alpha, and alpha should be equal to 4 radian per second. So 4, not radian, 4 revolution per second square. This is the value of the angular acceleration. Okay, this method is incorrect. Why is it incorrect? Because we can use this theta 2 minus theta 1 by t equal to omega only when can we use it? Omega is equal to, that is velocity equal to displacement by time. If I compare it with the linear ones, velocity equal to displacement by time. So when can we use this formula v equal to s by t? we can use it only when the velocity is a constant. Okay, so then only you can use S equal to Vt. Otherwise, you should not use. Now, what is happening here is a velocity constant. I'm going to replace this velocity with angular velocity, which is omega, and this S by theta, and this by t. Okay, so as a result of it, so if you do this one, omega equal to theta by t, this could be employable only when the particle describes equal angles in equal intervals of time. But what is happening here? The angle is increasing with respect to time. It is accelerating. When it is accelerating, then this would be incorrect. Did you understand the misconception here? The misconception here is that we came to know that we are using the incorrect parameters, okay, incorrect equations. Okay, as a result of it, you should not use this. Okay, so we had done so many problems in the mechanics part, in kinematics part, similar to this. Now here we are also doing the same type of problems. Only thing is I am going to replace this V with omega, S with theta. Okay, now as a result of it, we have to go with the equations of motion. Why equations of motion? Because you see uniform angular acceleration, right? So I'm going to use S equal to ut plus half at square. Instead of u, I put omega. Instead of a, I put alpha. T remains the same. I'll write it down if you want for your reference. S equal to ut plus half at square. So a, angular acceleration, linear acceleration, angular acceleration. Linear velocity, angular velocity, right? So here it starts from rest. Here also it starts from rest. So as a result of this, now we have to use this equation. Thus we have got an expression for alpha. Now the first part is done. Find the angular acceleration. Find the angular velocity. What is angular velocity? Omega final. Omega final. Now how do I find omega final? If you do not know the equation, the first thing that you can do is write down the analogous linear equation. What does the linear equation stand? Omega final is nothing but final velocity. Final velocity equal to u plus at. Now you write the analogous terms. Omega final for v. U, it is omega I plus a. What is a? A is alpha. T remains the same. Now what is omega I? Omega I is, we have used here. Omega I is equal to 0 here. Omega I is equal to 0 plus alpha. What is alpha? We already found 4 multiplied by what is t? Where is t? Where is t here? At the end of 5 seconds. 5 over here. So thus the answer should now be equal to 20. Okay. What is the unit? Unit is 20 revolutions per second. Okay. So as a result of it, the value of the omega at the end of 5 seconds is seen to be 20 revolutions per second, while this one is seen to be 4 revolutions per second square. So this is the correct answer. Friends, I think you would have got to know about this problem, how to solve it, what was the misconception here. The misconception here or the mistake here is nothing but the student had used the formula for the uniform velocity while he had to use the formula for the uniform acceleration. Okay, so let me stop here with this video, and in the next video we'll look more about the problems on rotation. Thank you friends for watching. If you like my video, do like, share and subscribe to my channel for more updates. Thank you.